In the previous lecture, we have seen the angular momentum operators, particularly the operators corresponding to the components of angular momentum and also the square of angular momentum. Now, our aim is to find the eigenvalues and eigenfunctions of these operators. So, in this first lecture on eigenvalues and eigenfunctions, we will see the eigenvalues and eigenfunctions of the operator Lz. Actually, this is very important problem, and you will find its application not only in quantum mechanics but also in atomic physics and molecular physics, where invariably this concept is used. And when you study nuclear physics, you will see again the application of this problem. So now let us try to find the eigenvalues and eigenfunctions of the operator Lz. You know, whenever we have to find the eigenvalues and eigenfunction of an operator, first of all we write the eigenvalue equation of the given operator. So here let us consider that psi of r theta phi is the eigenfunction of this operator and C is its eigenvalue. Then you know the eigenvalue equation can be written like this: Lz operated on psi of r theta phi equal to C times psi of r theta phi. This equation is nothing, this is simply known as eigenvalue equation, because you know in eigenvalue equation, whenever we operate the operator on the appropriate eigenfunction, we get simply the eigenvalue of the operator times the same function. So here psi of r theta phi, we have assumed that this is eigenfunction of this operator Lz, and C is its eigenvalue. As you can see, I have written actually psi as a function of r theta phi. It means we are talking about the spherical polar coordinates. As I have told you earlier, that actually in dealing with the problems related to eigenvalues and eigenfunction of this operator, the appropriate coordinate system or the convenient coordinate system will be the spherical polar coordinate system. So we will start with the expression for this or Lz operator in a spherical polar coordinate system. And you have seen in the previous lecture what is the meaning of this operator Lz in a spherical polar coordinates. So you have seen actually this Lz in a spherical polar coordinate system is defined like this: Lz is equal to minus IH bar del phi. This is just the meaning, or you can say definition, of this operator in spherical polar coordinates. As you can see, this operator Lz depends only on phi, not on r and theta. So using this expression for Lz in this equation 1, which is actually the eigenvalue equation of the operator Lz, we will replace this Lz by minus IH bar del phi. So this minus IH bar del phi will be operated on psi. So equation 1 now becomes like this. This is minus IH bar del psi by del phi equal to C phi. Sorry, actually equal to C psi, not phi. As you can see that here the differentiation is with respect to phi, not with respect to r and theta. So so for the differentiation purpose and the integration purpose, we will simply treat the variables r and theta as constant here. So you can say that since the differentiation is with respect to phi. So r and theta are treated as constant. For the purpose of differentiation and integration. So in this condition, there is no need to write the partial derivative. We can use the ordinary differentiation, keeping in mind that r and theta are constant. So in this condition, this equation 2 can be written as, you can see what we can write this equation. So after some rearrangement, equation 2 can be written like this. Equation 2 can be written as you can see, after some rearrangement you can write d psi by psi. See here, d psi by psi equal to c over minus I h bar. This is minus c by I h bar. But as you know, this 1 over I is equal to minus I. So this can be written as I over h bar c. And also d phi. C d phi. Now, as our aim is to find the function psi, and as in our equation d psi exists, so definitely we have to integrate it, because you know from calculus that if you know the differential of a function and your aim is to find that very function, you must integrate. So in this equation, as d psi exists and our purpose is to find psi, so definitely we have to integrate this equation. So after integration, what will be our result, you can see. So integral d psi by psi equal to, since IC over h bar, this is a constant factor, so this will be outside of the integral, and inside the integral there will be d phi. Now you know integral of d psi by psi, you know this is in fact ln psi, log psi, and this will be IC over h bar, and integral of d phi, this will be simply phi plus some integration constant, because you are doing the indefinite integration, so you must write here integration constant. Since in this equation in LHS there is log psi, so it will be more convenient to write the integration constant in logarithmic form. So write the integration constant as ln a. So you can say this ln a is what? This is integration constant. Now let us simplify this equation. When you will bring this log a in LHS, this will be simply ln psi minus ln a, and this will be equal to IC over h bar times phi. Now ln psi minus ln a, what will be this? This will be ln psi over a, because you know log a minus log b is log a by b, so this can be written as ln psi by a, and this is IC phi over h bar. So you can see this psi over a will be equal to what? This will be e raised to the power IC phi over h bar, and therefore psi is equal to a times e raised to the power ic phi over h bar, and say this is your equation 3. Now you can see here that as we have treated r and theta as constant in solving this differential equation, but psi you know is a function of r, theta and phi, because you know psi is equal to psi of r, theta, phi. But here directly in RHS only the variable phi exists, but psi is a function of three independent variables, that is r, theta and phi. So definitely this constant a must be a function of r and theta. So you can say that a is not an absolute constant, but it is a constant which depends on r and theta. R and theta. So we can say therefore as r and theta have been treated as constants, in solving the differential equation. So the constant a can be a function of r and theta, and therefore the eigenfunction for Lz will be what? So the eigenfunctions of Lz are. Now we will write psi of r, theta, phi, which are actually eigenfunctions of the operator Lz, and that will be equal to a of r theta times e raised to the power I c phi over h bar. Say this is your equation 4. So actually these are equation 4 defines the eigenfunction of this operator, but here C, which is actually the eigenvalue, have not been obtained till now. Actually all values of C are not allowed. You will see that there will be a particular restriction on the value of this constant C. Why there is a restriction on it, you can understand that actually the 2 points, if you consider 2 points, let us say r theta phi, and another point, let us say r theta phi plus 2 pi, then actually when the variable phi will change by 2 pi, there will be no change in this eigenfunction, because you know physically the point for which phi is equal to phi and phi is equal to phi plus 2 pi, they are actually not different points but the same point. So since at a given point the value of psi must be unique, so in this condition that you can say that psi of r theta phi and psi of r theta phi plus 2 pi must be equal, must be same. So the values of C are restricted. Values of C are restricted. Why? As the points r theta phi and r theta phi plus 2 pi are same. And as you know, the eigenfunction has a unique value at a given point in a space. So definitely we may write psi of r theta phi is equal to psi of r theta phi plus 2 pi, because these 2 points r theta phi and r theta phi plus 2 pi are not different points but same point, and at a given point the function psi must be unique. Its value must be 1 and only 1. So you can say that this psi of r theta phi and psi of r theta phi plus 2 pi must be equal. Now when we will substitute the value of these functions psi of r theta phi and psi of r theta phi plus 2 pi on the basis of this equation 4, what you will get? So you can see by the use of this equation 4, this psi of r theta phi can be written as a of r theta times e raised to the power I c phi over h bar, and this is equal to a of r theta and e raised to the power ic. Now instead of phi we will write phi plus 2 pi, you can see, and divided by h bar. So you can see this a of r theta and this a of r theta will cancel out, and your result is e raised to the power ic phi over h bar. This is equal to, now RHS can be written like this. This is e raised to the power ic phi by h bar times e raised to the power ic times 2 pi over h bar. Again you can see this exponential factor and this exponential factor will cancel out, and therefore you can say that e raised to the power ic times 2 pi over h bar will be equal to 1. So therefore e raised to the power ic times 2 pi over h bar is equal to 1. Now you can see when this equation will be possible, what will be the value of c or c over h bar, so that this result will hold, you can see easily. As you know, e raised to the power I theta, this is equal to cos theta plus I sin theta. So in this condition, this LHS may be written like this. This is cos 2 pi c over h bar plus I sin 2 pi c over h bar, and this is equal to 1. 1. Now see, In RHS there will be always 1 for all values of C over H bar. This will be possible only when C over H bar will have actually integral values. So you can see that this equation will be satisfied only when C over H bar is an integer, and this integer may be positive, may be negative, or even may be 0. So hence C over H bar must be equal to M, or M is equal to integers. It means M is equal to 0 plus minus 1 plus minus 2 plus minus 3 and so on. Only then this equation will be satisfied. You can check. When you take M equal to 0, then you can see that this C over H bar will be equal to 0. So cos 0, this factor will be 1, and sin 0, 0. And if you take it to plus 1, then this will be cos 2 pi plus I sin 2 pi. But sin 2 pi you know is 0. So you can see when we consider C over H bar equal to M, where M is actually integers like 0, plus minus 1, plus minus 2, plus minus 3, then this equation will be satisfied. So on this basis, you can say that this C over H bar is equal to M, where M are integers. And therefore, what will be C? C is equal to MH bar. C is equal to MH bar. So you can see that these are actually the values of C. And what are C? You know, C are actually the eigenvalues of our operator Lz. So you can say that eigenvalues of operator Lz are MH bar. Remember it. This is a very useful result, because when you study atomic physics, particularly the atomic spectra, then you always find the use of this result, that is the eigenvalues of operator Lz. So you can say, eigenvalues of Lz are, when you take M equal to 0, this will be 0. If you take M equal to plus minus 1, this will be plus minus H bar. When you will take M equal to plus minus 2, this will be plus minus 2H bar, and so on. So these are actually the eigenvalues of the operator Lz. Now finally you can write the eigenfunctions of this operator Lz. So thus eigenfunctions of Lz are psi of r theta phi, and this is equal to A of r theta, and e raised to the power, you can see it here, this is e raised to the power ic phi by h bar. But c over h bar, you can see this is equal to m. This is equal to m. So you can write e raised to the power im phi. So this equation 6 actually defines the eigenvalues of this operator Lz. And this equation 5 defines its equation 6 actually defines the eigenfunctions of operator Lz, and equation 5 defines the eigenvalues of this operator L. Now one thing is very remarkable here. Let us see what will be actually the degeneracy of this of the eigenvalues of this operator Lz. You can easily see degeneracy. Degeneracy. Now you can see, if you will choose the different functions a of r theta, but this factor e raised to the power im phi will kept at a particular value, and we choose the different values of this a of r theta. In fact, in that condition, we will have the different values of these eigenfunctions psi r theta phi corresponding to the different values of this a. Although e raised to the power im phi remains same, but due to the various values of this a r theta which we will select, we will have actually the different values of psi r theta phi. But for all those values of psi r theta phi, since m has been taken same, so this eigenvalue will remain same. What does it mean? It means you can say that we may have infinite number of independent eigenfunctions of Lz with the same eigenvalue mh bar. So in this case, you can say that actually this each of the eigenvalue of this operator Lz is infinite fold degenerate. So you can say by choosing different functions, a of r theta, but keeping the part e raised to the power im phi unchanged. We may have infinite number of independent eigenfunctions of Lz with same eigenvalue mh bar, because m is same. So in this condition, you can say that each eigenvalue of the operator Lz is infinite fold degenerate. So our conclusion is what? Each eigenvalue of Lz is infinite fold degenerate. This is a very remarkable fact. Now we will see another remarkable fact regarding the eigenvalues and eigenfunctions. In this lecture, you can see we have obtained actually the eigenvalues and eigenfunctions of the operator Lz. But we have also defined two operators, and those are Lx and Ly. So if you want to find the eigenvalues and eigenfunctions of these operators Lx and Ly, what will be those? In fact, there is no need to find separately the eigenvalues and eigenfunction of Lx and Ly, because the eigenvalues and eigenfunctions of the operators Lx and Ly are same as that of Lz. But can you say why the eigenfunctions and eigenvalues of Lx and Ly will be same? In fact, the eigenvalues and eigenfunctions of Lx and Ly and that of Lz will be same because all the directions in the space are equivalent and any direction can be chosen as z-axis. So the eigenvalue of operator Lx and Ly will be also mh bar, and their eigenfunctions will be also ar or a of r theta e raised to the power im phi. So Lx and Ly eigenvalues and eigenfunctions of Lx and Ly are same as that of Lz. Because why this is possible? Because all directions in a space are equivalent and any direction can be chosen as z-axis. Any direction can be chosen as z-axis. In fact, when we will study the generalized definition of angular momentum operator, then you will see that the eigenfunctions of these operators are written in a particular manner in Kate symbol. So in Kate symbol, the eigenvalue equation of Lz is written as Lz Lz ket Lm is equal to mh bar ket Lm. Actually here this ket Lm, this is eigenfunction of Lz, and mh bar, these are eigenvalues of Lz. Actually here this L is a quantum number and this quantum number determines the value of m. Actually L has value 0, 1, 2, 3 and so on. These are actually non-negative integers. Non-negative integers. Actually when we will express the eigenvalue equation in matrix form, then this notation will be more useful, and we will talk about these notations for the eigenfunction in the forthcoming lectures, when we will see the generalized definition of angular momentum operator in quantum mechanics.